Okay, so this video is picking up where we left off before. We had this beautiful decomposition of a matrix A into um, a sum of rank 1 matrices by using the SVD. And we're going to see a couple of applications of the SVD. Today we're going to be talking about the generalized inverse. And then in another video, we're going to be talking about doing a little bit of image processing, just for some fun. Okay, so let's talk about the generalized inverse first. Let's get things set up. So we're given A that is m by n, and let's suppose we know that that has rank k, and we're trying to solve ax equal b for x. Right? Now, let's think about things in terms of the four fundamental subspaces: row space, column space, null space of A, null space of A, null space of A transpose. That was sloppy. We don't usually use the null space of A transpose, but okay. Now, this is going from Rm to Rn, and because m and n are typically not the same number, we would have to say that this mapping x to ax is not invertible, right? It can't be invertible if you're mapping two spaces that are of different dimensions. Okay. However, I'd like for you to think about this. If this matrix has rank k, then the dimension of the column space is k, and the dimension of the row space is k. And so if you restrict the mapping to be between the row space and the column space, right? Now you're mapping a k-dimensional space to a k-dimensional space. And this mapping, restricted to these two spaces, should be invertible. And so that's the mapping that we're going to be looking for. Okay, so how am I going to do this? Well, number one, if I have a y vector that's out here somewhere, or a b vector that's out here somewhere, I'm not going to be able to solve it anyway, so that's going to need to be projected to the column space of A. And so in order to do that, I'm going to need to have a basis for the column space of A, right? Where am I going to get that? The SVD gives you your U. And similarly, by the way, that's just the first k columns. That's the basis for the column space. Similarly, for the row space of A, that's dimension k. Where do I find a basis for this row space? Yes, it is the SVD. Of course, the SVD gives us everything. And that's the first k columns of E. Okay, so our mapping now is going to be between this space, the space spanned by the first k columns of V, and the span of the space and the space spanned by the first k columns of U. Very good. Okay, and so what's going to happen then is that we're going to be looking for an x that's also just in the row space, right? I'm not going to be worried about the null space at all of either space. So I'm just going to be looking for a solution to this is going to be in the row space, and the b that I'm going to be looking for is actually in the column space, not going to be out here. Okay, good. So that's the idea behind it. Okay, so now suppose that I've got U sigma V transpose is the SVD of A. I'm kind of writing this in MATLAB notation there. In fact, I don't even have to write that. Let me just write A here. Then, if I have A times X equal B, then I can replace A by the SVD. Right? And now this is the full SVD here. This is not the reduced SVD. Although, you know what? Let's go ahead and say that this is the reduced SVD. So U is going to be M by K, and then sigma is K by K, and then V is N by K. And by the way, notice that if we have rank K, that means that sigma is diagonal and square and invertible. Okay, we're going to talk about this more in just a second. But let's look over here. So this is going to be M by K. And so what happens if I multiply both sides of this equation by U transpose? U transpose is going to be K by M, right? And so if I feed that through, U transpose U is the K by K identity, and so this becomes sigma times V transpose times X equals U transpose times B. Good. Now let's discuss this diagonal matrix. Does everybody know how to invert a diagonal matrix? So suppose I've got a matrix that's 2, 3, 0, 0. The inverse is actually going to be 1/2, 1/3, 0, 0. In other words, the inverse, by the way, you could double check that by multiplying those two out. I'll let you do that. The inverse is the reciprocal of each diagonal element, and so it itself is diagonal as well. Okay, so this is like an example sigma, and this would be how you compute sigma inverse. So when you have a diagonal matrix, it's really easy to invert it. You just take the reciprocals. And so that's what we're going to do next, is just multiply both sides by the inverse. And just to keep track of sizes of things, these are K by K, right? K by K. And so that's a K by K identity matrix. That's sigma inverse times U transpose B. Okay? So those cancel, giving you the identity. And finally, what are we going to do? Let me rewrite that. Good. Finally, we can multiply both sides by V. And so V is N by K. NKX, no, N by K. V transpose is K by N. X is N by 1. Sigma inverse, let's just go ahead and get them all done here. U transpose is M, or K by M, right? And then the B is the M by 1. Good. And so now you see here, when you multiply this out, VV transpose is V transpose equal to the identity? Ooh, I hope you said no. What is it? It's the projection matrix into the column space, let me not say that, into the space spanned by columns of V. Okay, and that is the row space of A. Good. So on this side, I can't simplify it any further. I could say this is VV transpose times X is equal to V times sigma inverse times U transpose times B. Right? So this, let's just call this X hat. The idea here is that X hat, if this is my RM here, this is my null space of A and my row space of A. What I'm saying here is X might have been out here, but we're forcing X to be in the row space, right? So this is our X hat here, and this was the original. This is the possibly original x. So this is no problem. We can just say this is just going to be the projection of x onto the row space. And here, this function, or this matrix product here, is the Moore-Penrose pseudo inverse. And so notice how that got constructed, right? So if A is equal to U sigma V transpose, then this is the reduced SVD. By that I mean rank K. Right, then you construct the Moore-Penrose pseudo-inverse by taking A, this is a dagger, and that's equal to V sigma inverse U transpose. So notice that you go in reverse order and take the inverse of the sigma. Good. And so again, that's called the Moore-Penrose pseudo-inverse. So let's go back to the original equation now. If I have A times x equal B, then to solve it using the Moore-Penrose inverse, I'm just going to take a dagger and multiply by both sides. And now we see, right, that if I take a dagger times a times x, I may not get x, I'm just going to get the projection of x into the row space, but that's fine. That gives me an x, right? But on this side, this should be this should give me the least squares solution, I'm trying to say, because B should be, I'm not going to be able to solve this, right, if B is sitting outside. Oh, where's my, did I miss it already? There it is. If B is sitting outside of my column space, I'm not going to be able to solve the equation. So in that case, right, this would be a least squares solution. Okay, this is going to be a least squares solution. If B is not in the column space of A. And we will show that, actually we're going to show that in the exercises, so I don't want to give that away. Yeah, let's stop there. Because, let me just show you how that's going to work. Right, because now that I know that my x is going to be a dagger B, and if I rewrite that, that's going to be V times sigma inverse times U transpose B, right? So what happens if I take A times x? That's going to be A times A dagger times B, right? And so that's going to be U sigma V transpose times V sigma inverse. Oh no, I think I did put this in the assignment. Oh well. U transpose times B. Let's simplify that. V transpose V is the identity. Sigma times sigma inverse is the identity. And so you're left with U transpose times B. So A times X is U transpose times B. Is that right? Absolutely, that's right, because A times X is in the column space of A, and this is the projection of B onto the column space of A. Very good. Okay, I think I've already done one of your homework problems. Okay, so in the next video, we're going to talk about something important, but something that we're not going to do very much of right now, and that is, remember that everything that we've done so far was based on knowing the rank K. So I'm just going to say a couple words about the rank in the next video, and then the third video after that, or the next video after that, will be the video about some image processing. Okay, see you later.